Our next speaker is Payam Zahadat, who's going to be telling us about reactive or stable, a plant-inspired approach for organization morphogenesis.
Do you see my slide?
Yes, we do.
Thank you. Hello, everybody. As you can see in the title, this work is about a plant-inspired approach for organization morphogenesis. And by organization, I mean business organizations or human organizations. So if we have a look at plants and business or human organizations, we actually see quite some similarities, at least at the structure of such systems. Basically, both systems are hierarchical systems that grow autonomously based on continuous resource intakes, and these resource intakes are dependent to the environment, so both local and global environment. And these systems have feedback between emerging shape of the structure of the system and the local environment. So the focus of this work is mostly on the shape adaptation to local resource availability for the system. In the long term, our research objective is quite a long run, basically. And we try to go towards a generic theory of adaptive growth in hierarchical systems based on some extensive cross-domain studies. But in the short term, this is much more modest objective, basically. So this is basically a first step that we first try to transfer a plant growth model to a human organization. And we also have a look at the impact of resource sharing level, meaning the strategy for the resource sharing and competition in the system between branches of the system on the shape formation and adaptability in dynamic environments. So let's have a look at plants first. Plants are not so famous for their swarm and collective behavior, but one can actually see them as, so all these branches of a plant can be seen as autonomous agents which in a self-organized process, they shape the structure of the plant. So by competition and collaboration between these autonomous agents, we get a shape for this plant. Also, there are genetically encoded parameters which are important here. So if we have a bit closer look at how plants work, we have one important thing, which is the distribution of common resources. So there are common resources like water and minerals for plants, and these are supposed to be distributed all over the plant, so between all the branches of a plant. And this distribution is via vascular strand. So all the vessels in the branches, they do this distribution. And branches actually compete with each other for getting these common resources because the resources are limited. And if somebody makes more vessels, some branch makes more vessels, it would get more resource, and therefore it can grow further. On the other hand, the way this competition works is that at the tip of each branch, there is some hormone which acts as an information signal. And this is produced based on local conditions. For example, how much light this branch has access to. And this information signal, this hormone, is when it is produced, it flows towards the roots along these vessels that I mentioned before. And during this flow, when it flows towards the root, it tunes the thickness of the vessels. So basically, if some branch is in a better local, has a better local conditions, it would produce more of this hormone, which means it would get thicker vessels, and thicker vessels would mean a larger share of this limited common resource. So it would grow further in these better areas, while somebody in a less favorable area would get less of the resource. So we have put all of this together, and in a very abstract model called vascular morphogenesis controller, or VMC. And this VMC is a growing directed acyclic graph where each connection has a weight. So we have like these connections act as the vessels, which I mentioned before. And the weights of these vessels are tuned based on a signal that is produced at the leaves of the graph. And this is produced based on local success of the leaves. So basically the success can be anything. Whatever the agent at the tips of this, at the leaves of the graph can achieve, depending on how we want to use the graph basically. But again, similar to the real plants, locating in a more favorable region would mean more success, would mean more or thicker weights for the vessels, and that means a larger share of the resource for the branches. So if a very large amount of resources available at some of these tips, some of the leaves, the leaf is allowed to grow. That means it would get new nodes. So the system would, the structure would change. And this change in the structure in the morphology means changes in the success flow. So a different amount of success would be produced at this point. And that means a change in the vessels, and which follows up with changes in the resource distribution. If, on the other hand, some part of the structure gets too little resource, because the resource is limited, it can happen actually only because somebody else is in a very good position. So in that case, this part of the structure might start, and the nodes would be deleted. So the morphology would change. It is valid also the other way around. So we can remove something, and that could end up with a growth in a better position. Basically, we have a feedback loop. So changes in the amount and distribution of resource may lead to changes in the graph structure, addition or deletion, and the other way around. So I'm not going into the details, but just there are 2 points which I would like to tell you. One is the resource distribution. As I mentioned before, every node would distribute the resource which is available for that node between its children. And the node can itself also consume some of the resource, and the rest would be proportionally to the base of the children distributed between them. The other point is the vessel update. So how the vessels change. The vessels change toward a function of the success flow which is passing them. So here the function is a power function. So we have an exponent of beta, which we call it a competition factor. And the reason that we call it competition factor is that it actually determines how much competition between the sibling nodes would happen. So if beta is 1, it is directly correlated with the base distribution of the resource. And if beta is lower than 1, we will have lower competition, more relaxed competition, because the differences between the siblings is lower. And if beta is higher than 1, we have intensified competition, and we encourage competition, and we intensify the differences between siblings. So this VMC system has been used in different scenarios so far. So before we have used it in swarm robotics, in real robots, and the simulation, and like different artificial life scenarios also in previous conferences. But here we are more interested to see how would it compare in a organization, so human organization. So as you can see, we have the VMC in a plant and we have a VMC in an organization, and they can be used comparatively. So here in the organization, the leaves that I mentioned before, here we would call it service units, and they produce some profit. So the success here is the profit that the service unit would produce providing services to customers. And this profit depends on the type of the service, the demand for the service, and the number of nodes which provide this service. Also, similar to grants, we have a common budget. In this case, the common budget is the aggregation of all the profit made by these service units, and plus an external budget can be also added. For example, we can have some initial investment for some time just to get the system started. The intermediate units, they consume some of this budget, this resource that they receive, yeah, they consume it as administrative overhead, and larger amount of budget at the tips might lead to division of a unit into several units. So we can have growth here, and also we can have removal of some subunits. So the morphology of the organization would change similar to a plant. So we have an example scenario here. We have an organization structure changing in a example dynamic environment. The structure starts here for the visualization. We have combined all the factors of profit making in these colors, and the brighter color means more profit. So the structure starts, it grows after some time to this structure, and then we switch the environment to an opposite, and the structure adapts to these new conditions. We switch it again, and it adapts again, and again we switch it. So what is maybe interesting to have a look is that over these switches there are differences. So some parts of the structure would stay still in the in the areas which are not that interesting anymore. But the system keeps some parts of the structure because they still provide some, produce some profit. And this helps actually the system to grow even further than before. So here you see the this change in the profit and the whole budget of the system over time in these 4 switches. So there is this nice jump here. But this is actually with one parameter setting. So we were interested to see what is the effect of the competition factor. So the strategy of if we want to have more competition or less competition, if we want to distribute things more uniformly or not. So here you see 5 different values for the competition factor. At the left side, you see a very low competition factor. So the budget is distributed quite uniformly over the whole system. And on the bottom, you can see the last steps in after each switch, basically. So you see that for the very low competition factor, we have a quite a stable structure, but it doesn't actually grow that much in the more interesting areas. When we increase this competition, we would have more adaptation, but the system is not as stable. So that means we have changes, more changes in the restructuring and reallocation of the nodes. At this, at the middle 0.9, we have maybe the highest adaptation, but there is also quite some restructuring. When we go higher, 1.1, we have even more competition. So the system tries to get a lot out of the environment. And one more interesting point is that the final case, so 1.2, which is quite a greedy system. So the system is so focused on getting highest profit, which is making now, that it cannot really adapt to the changes in the system. So what is made here is enough for the system, and it doesn't really let itself to allow itself to have a look at the other side, which is now a better place to grow. So we can have it with a faster pace of switching, and we see similar traits. And I would just wrap it up. We have a plant growth model and try to transfer it to organization adaptation in dynamic environment. We studied the impact of resource sharing level between branches. So sharing everything or like too uniformly may lead to missed opportunities and limited growth. And if like too much competition may lead to monopoly and limits adaptability. And the optimal would be a middle ground competition for each environment. And in the future, we would introduce adaptation costs and delays and so on. And we would also like to have to study well-established organization models to see where our model would locate actually. Thank you. And if there is some questions.
Thank you very much, Payam. If anybody has a question for our speaker, please go ahead and unmute yourself and ask your question.
Hello.
Yep.
Yeah, thank you very much for very interesting work. So I joined in the middle of your talk, so I might have missed some point. My question is about the evolutionary adaptivity of the optimality. The optimal value of beta might actually depend on how dynamic the environment is, right? Yeah. So if the organization does not have the prior knowledge about how fluctuating the environment is there any way that they can actually learn the optimal value in the process?
So in the current model, we don't have something like that. But yes, so in general, we can have, like we have some thresholds, for example, for adding or removing parts of the system. These thresholds can be easily dependent on the situation, like depending on the previous changes, basically. And also some other parameters can be adapted. So we can have evolutionary algorithms, basically. And also I would see some ways of learning, like a reinforcement learning kind of type of thing that